Dear students, let us continue our D&F block discussion. I will go to another property, complex formation. Complex formation or coordination compounds. Complex means coordination compound. We have a lot of examples where coordination compounds are formed by transition metals. Copper sulfate, copper H2O for sulfate. This is a copper sulfate. Lot of examples are there. Particularly transition metals are forming the coordination compounds. We have in a chapter where we will discuss the details of coordination compounds. I would like to introduce you uh, how or why transition metals and inner transition metals forms coordination compound generally. What are the peculiarity that will help transition metals to form the coordination compounds? These are the characteristics. One is its small size. Small size means smaller size compared to alkali metals. Second is they have a high charge. They have high positive charge. You have Fe3 plus, Fe4 plus like that. Third, they have more polarizing power. Polarizing power. This is associated with the charge, more polarizing power. Then they have variable oxidation numbers. They have variable oxidation numbers. They shows variable oxidation numbers. Now there is an availability of vacant d orbitals. Availability of vacant d orbitals. I just give you one point. The complexes coordination compound of +3 oxidation state is more stable than +2. Coordination compound of +3 is generally considered as more stable than +2. Because of these features, transition metal forms the coordination compound. Now, alloy formation. Transition metal forms alloys. Alloy formation. Transition metal forms alloys. What are alloys? Alloys are solid solution. Solutions are different types. Solid solutions are there. That is, solid solution means solvent is solid, solutes also solid. That is, it is a homogeneous mixture of alloys are homogeneous mixture of homogeneous mixture of two or more metals. These are the homogeneous mixture of two or more metals. They are called alloys. We have a lot of examples. Let us take some examples. Name and their examples. Alloys. Compounds. Brass, copper and zinc. Bronze, copper and tin. German silver, copper, zinc nickel. Rolled gold, rolled gold. Copper, aluminum. Stainless steel, stainless steel. Iron, nickel, and carbon. Nickel steel, nickel steel, iron, nickel. These are the important alloys of transition metals. Not only transition metals are forming the alloys, S block elements also forming duralumin. It's another kind of alloys, that is magnesium, aluminum, etc. There are a lot of alloys. I just give you some examples of alloys which formed by transition metal. Why transition metals forms alloys? Why transition metal forms alloys? That's the question. Why transition metal forms alloys? Why? Because of similar size of transition metals. Transition metals. Uh, different metals can occupy lattice. Look at here. Suppose this is a lattice. Lattice is nothing but a three-dimensional arrangement. Suppose it is this is different kind, homogeneously arranged. Okay, like that, homogeneously. It goes on. Therefore, lattice one. This is a metal layer. This is B. Okay, B, 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 B. All others are A. Because of small or similar size, almost equal size, they can be occupied in the lattice points. Okay, that's all alloys. Now another one is interstitial compounds. Interstitial compounds. Interstitial. Transition metal forms interstitial compounds. I just write like this. Interstitial compound, example FeH 0.9 or chromium H like that. It is the compound. It is the heterogeneous compound. Heterogeneous compound where small elements like carbon, hydrogen, oxygen are occupied. Small elements like carbon, hydrogen, oxygen are occupied in the interstitial void, in the interstitial voids. The interstitial voids. Suppose you have an elements like this. Small elements like carbon or hydrogen are occupied here. This is the interstitial compound. Interstitial compounds and alloys are different. Alloys are different metals are in the lattice points. Here the second elements are in the interstitial voids. You understand that difference? In alloys, different elements are in the lattice points, but here different elements are in the interstitial voids. Properties of interstitial compound. They have a high melting point. Properties of interstitial compound: high melting point, high boiling point, chemically inert, they are very hard. They are very hard. They are non-stoichiometric. They are very hard. They are non-stoichiometric. They preserve. They have. They preserve metallic electrical properties. Electrical properties. These are the interstitial compound. High melting point, high boiling point. They are chemically inert. They are hard. They are non-stoichiometric, etc. Please understand difference between alloys and interstitial. Alloys will be like this. In the case of alloys, this is the second element. Second element will be in the lattice points. This is A, this is B. B also in the lattice point. Here the second element in the interstitial voids. Okay. Yes. Therefore, that properties are over. Now we can go to the magnetic properties. Transition metals are magnetic. Magnetic properties. Magnetic properties. Many transition metals are magnetic. They are I will tell you, they are paramagnetic, para or ferromagnetic. Ferromagnetic. Okay. One of the best examples CrO3. It's a ferromagnetic. Okay. Magnetic property is measured by magnetic susceptibility. That is chi. Chi is equal to B by H or M by H, where M is equal to magnetization ability, H is equal to external magnetic field. What is a magnetization ability? It is the measure of M is equal to measure of ability of a substance, to take up magnetization, measure of ability of a substance to take magnetization in the applied magnetic field. This is measured by Gauss method. By Gauss method. It's a measure of ability of a substance to take up magnetization in the applied magnetic field. This is measured by Gauss balance or Gauss method. What is our Gauss method? Gauss method, that is magnetization, is measured by Gauss method or Gauss balance. What is the magnetic susceptibility? And magnetic property is also measured by Gauss method. It's a balance. That is, we have a balance like this. Okay. We have a method like this. Here you have a balance like this. Here also we have hanging setup, and we will hang our compounds here, north pole, south pole. This is substance. Now here we will add the weight. Now here is the substance. Now if you add a paramagnetic substance, what happen, this, if this material substance is paramagnetic, this external magnetic field, this is external magnetic field, or a bar magnet, external bar magnet. If this is paramagnetic, external bar magnet will attract them. Because of that, this side will feel more weight, and this needle or pointer will come to this direction. That is, if this is a paramagnetic, this will be attracted more by external magnetic field. Therefore, this side will feel more weight and needle will be this side. Therefore, we will understand that it is a paramagnetic. Now, if it is a diamagnetic, it will repel. When it repel, this will be pull out. Therefore, this side will be less weight and this side will be more weight. The needle will move to this direction. Therefore, this balance will tell you whether the substance is paramagnetic or diamagnetic. If it is paramagnetic, needle will be here. If it is diamagnetic, needle will be here. If it is paramagnetic, it will be more attracted and this side will feel more weight. If it will be diamagnetic, this side will be repelled and it will be less weight. This is all about the magnetic property. Okay. Therefore, we have discussed magnetic property, alloys, complex formations, etc. Now I will go to oxidation state. We have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. I think this topic is already discussed. Let us check it, and next video we will come to the chemical properties. Thank you for watching.